Ah, there we go. Okay. So if somehow you just have a single moving charge, we know that force is QV cross B, right? Well, usually you don't have a single moving charge. Typically, when you got moving charges, it's because they're running through a wire, and then you have a current, right? So let's look at the QV part of it right here. Well, V is like distance over time, right? So this is Q times, I'm just call it L over T, where L is like the length moved, but as a vector, I care about the direction, not just the distance, right? Well, what's Q over T? I mean, what is a current? A current is moving charge, right? So that Q over T, that's just current. So if you have force on a wire, and my pen quit working. There we go. It's just going to be, well, do the current, and then instead of V, do the actual length of wire across B. So for college physics purposes, this is going to be ILB sine of the angle between the wire and the magnetic field. So angle between the wire and the magnetic field. All right. Let's go back to the problem. They give us the current, give us the magnetic field. Current's going down. What's the direction of the magnetic force if the magnetic field is towards the east? Okay, so first let's get the direction right. So the current is going down, and the magnet, so this is the wire. The magnetic field is going to the east. So if I go I cross B, again, this is right-hand rule. Let me stand up and actually put my right hand on the board. So if I go I cross B, you want to put your right hand on I with the palm facing towards B. Right hand on I, palm is facing towards B. The thumb is pointing out of the board. So if they said B was going east, so if B is east, that means out of the board would be south, right? So this should be south. Actually, okay. I was going to say it might be north because I never know if, yeah. For a second, I was a little scared because I was thinking, oh, but the electrons are negatively charged, but it doesn't matter. They told us the current is 1.35 going, so it's fine. So, okay. What's the magnitude? Well, the magnitude is the easy part. It's just I times length times B, right? So the I we got, the B we got, and the length is 1 centimeter. 1.35, whoops. 1.35 times the length is 0.1, no, 0.01. Times 0.56. That's 0.00756. Okay, now if the wire is toward, if the magnetic field direction is toward the south, well, nothing has really changed at all. The only difference is now this is pointing south instead of pointing east. So straight out of the board, if B was pointing south, would be to the west. Right. It's now going west. And the magnetic, well, the angle hasn't changed. I mean, you still have the wires perpendicular, so it's still going to be the same force. So 0.00756. Okay, so now something's going to be a little bit different. So well, actually, no, it's not. Because south of west is still, I mean, the field is still going like horizontal, and the thing's still going down, so the angle between them is still 90. So I just have to draw a little picture. Give me a second. Yeah, it's just one because the magnetic field is perpendicular to I. And it's still perpendicular to I on this one. It's just now that B is pointing 10 degrees south of west. So if let me draw a little picture. Here's 10 degrees south of west. If I rotate 90 degrees, I get 10 degrees and 80 degrees. So this is 80 degrees north of west, or 10 degrees west of north. How do they want us to say it? They want the angle's value north of west, so it's 80 degrees north of west. Let's go back to the picture in case that didn't make sense. So they said it's 10 degrees. We start 10 degrees south of west. And then just like the others, we're just saying, okay, if you rotate 90, so rotate 90, you wind up here, which they asked for the answer is an angle north of west, so that's 80 degrees north of the west. I always thought those sorts of directions are confusing. Why can't we just say, oh, that's a 100-degree angle? That would be so much easier. What's the magnitude of, okay, and again, since the current is still perpendicular to the magnetic field, the sine theta is still 1, so it's still 0.00756. All right, so now let's go find that 5 since we took care of all the easy ones. We're ready for the hard one. It probably is just drawing a picture or something. Nope, it's not drawing a picture. That's a little bigger than I thought. Okay. Between the poles of a powerful magnet, actually, let's start a new video. Oh, no, that's not what I wanted to do. Share screen. Share screen.